Okay, so this is a video on how to graph transformations of sinusoidal functions. So again, sinusoidal functions is sort of a generic term to represent either a sine curve or a cosine curve. So really the main success criteria that we're looking for this in this section is just given an equation of a function, of a sinusoidal function, or a description of it, is that we want to be able to graph it. So as we recall back in just transformations of any functions, it could be broken down into what I call the A, K, D, and C attributes of the function. And the K value, it really affects the horizontal stretch or compression of our function. And how it relates to a sinusoidal function is that we know that this affects the period. And we'll talk a little bit about that a little bit later on. D is what we refer to as or affected the graph in terms of shifting it left and right. But when it comes to sinusoidal functions, we describe that as a phase shift, either left or right. And then A value, in generic functions, the A value does a vertical stretch or compression. But when it comes to sinusoidal functions, we know that the A value also is the amplitude of the function. And also we need to look at whether there's a possible reflection in the x-axis as well. And finally, we have the C value. In other words, we're adding something outside our function, and this defines our vertical shift left and right, up and down. And in our sinusoidal functions, although it's not written here, we know that it's going to affect our equation of axes. So in general, if we have a sinusoidal function, it can be broken down into, if it's sine, you broke down into that kind of format. So an important thing over here is that we always factor out the k inside our function that's being multiplied to x. So that applies to everything in general when we look at transformations, and we have to do that for sine and cosine as well. And there is what cosine would look like, and notice that everything is the same. So one of the things that we kind of remember or refresh is that sine and cosine curves, they really are the same. It's just a shift left and right. So therefore the amplitude will always be the same, the equation of axes will always be the same, as well as the vertical shift will always be the same. So when we describe a graph, either sine or cosine, we really need to understand what the actual phase shift is given that function. Okay. So when we go through this, again, so here's a review. When we have the period, if we're given the k value, the formula is the period is 360 divided by k. Again, the amplitude is the a value. So if we're given the amplitude, we're automatically given the a value. If we're given a phase shift, that's the d value. And if we're given a vertical shift, that's really the c value. So when we're sketching curves, we'll label the axes according to the scale. So one important thing is, how do we determine the scale? So if we just look at a generic or parent functions of sine and cosine, we're going to do this, or I would do this often, just to get a visual of what the parent function looks like. So in case of sine, it starts at the equation of axes, it goes up, so that would be 90, 180, 270, 360. It's going to start the equation of axes, go up, come back down, go to the trough and back. So it looks something like that. Okay, and notice that within there, the sine curve can be broken up into 4 equal parts. So it kind of makes sense when we did the trigonometry and looking at on the grid, we have 90, 180, 270, 360. So exactly 4 equal parts, and that's what the curves will always look like. So how can we determine how can we determine the scale? So we're going to say that the scale is always going to be whatever the period is, and we're going to divide it by 4. So that's one easy way when we go off from graph. It determine the scale is once we figure out what the period is, that's just going to be the graph broken up to 4 equal parts. So here, let's get to some examples. So here's a sketch. And Again, here's our equation. And the first thing I notice is that there's a k value, and so we're going to factor out the k value. So in this case, we're going to get y is equal to minus sine of 3 theta plus 60 degrees plus 1. Okay, so off to the side, I'm going to exactly list what my a, k, d, and c values are. So my a is, in this case, as a minus 1, k is 3, d, my horizontal shift, again, how I think of this is what makes inside that bracket there, what makes that 0. That's going to be negative 60, so this is going to be shifted 60 degrees to the left. And then my c value is 1. So let's go off and sort of, these are hints to sort of what the things that we need in order to graph our function. So in this case, the period, again, it's going to be 360 degrees divided by my k, which is 3. So my period is 120 degrees. So once I determine my period, then I know that my scale is going to take that divided by 4, so 30 degrees. So basically every single tick on my x-axis, this is going to be 30 degrees. So I'll just label that now. And 180, and because I know this graph is shifted to the left because my d value is negative, I'm going to label on the other side as well. My phase shift, so in this case we see that it's going to be 60 degrees to the left since d is negative. The amplitude, again, I'm looking at a, so here amplitude is always positive, so we really want to take the absolute value of a. So it's really the absolute value of a. In this case, is the absolute value of negative 1, which is 1. So amplitude is always positive, just like a stretch factor or a compression factor is always positive. In this case here, a vertical shift is 1. So that implies that my equation of axes is y is equal to 1. So once we determine that, we always want to draw the equation of axes. That's going to be really important because once we know the amplitude, we know the amplitude is always a distance away from the equation of axes. So let's go off and graph this. So we know that here we're talking about sine. Sine starts at the equation of axes. So that's really important. So it starts right here. So this one is actually a tricky one to start off with because here we actually have, because a is negative 1, we actually have a reflection in the x-axis. So in order to see what a reflection looks like, let's look at what the parent function of sine looks like. So I drew it above, but I'll draw it again because we really want to get in the habit. It starts in the middle, goes to the peak, down to the middle again, down to the trough, and back up. So it'll look something like this. So hopefully you can see that when we reflect this in the x-axis, what happens is that while the middle still reflects back to the middle, but the peak becomes the trough. And then the middle is still the middle, the trough becomes now the peak, and that was reflected over the x-axis, and the middle stays in the middle. So the reflected sine curve, instead of going up to start with, it actually comes down, goes back up, and looks like that. So that's how we want to label our points or plot our points, is that from the equation of axes, instead of going up by an amplitude of 1, we're actually going to come down. So we actually come back to the x-axis, and then we come back up. So notice that here, because we did our scale divided by 4 in those 4 equal parts, that's why I'm doing the ticks for each point. So we get down here, so sine comes back to the middle. In this case, because it's reflected, we go up to the peak and back down over here. So here I connect it through a nice curve, and that's our graph. So here we have y is equal to negative sine, and I'll just copy the equation again. If I use function notation, then I could have just written f of x or something like that, but because I didn't, we're going to write the entire equation. So that's what that graph kind of looks like. Okay. So the next example is one of cos. So once again, you have a k value here. So this one looks really weird This one, you can think of it as really 1/2 theta minus 180 degrees. So here we really want to factor out a 1/2. So this is the same thing as y is equal to 3 cos. We factor out a half, so this one's a little bit tricky. We get theta minus 360 degrees because 180 divided by a half is the same thing as 180 multiplied by 2 minus 2. So I'm going to list off my attributes again. A is 3, K is 1/2, D is 360 degrees. So it's positive because again, what makes that 0? And my C value is -2. So let's fill in the other things here. So we determine the period. The period is going to be 360 divided by K. So in this case, it's 360 divided by half, which is the same thing as 360 divided by 2. So that's going to be 720 degrees. So the scale, we're going to take the period divided by 4. So 720 divided by 4 is 180 degrees. And so now once I have that, I'm going to go off and label my scale. So 180, or so I label my x-axis, or put the scale on my x-axis, 360, 540, 720, and I'll just keep going, 900, and 1080, and on the negative side, -180 degrees, -360. Although I can see this being shifted to the right, I probably don't need to label this the scale on the left. Here we have a phase shift, is 360 degrees to the right, since D is positive. The amplitude is 3, so the absolute value of 3 is just 3. And here we have the phase shift is -2, so that means our equation of axes is y is equal to -2. And again, highly encourage you to draw the equation of axes on our graph every time we determine it. So this time I'll do this in purple. So there's my equation of axes. And cosine. So let's take a look at, again, a reminder of what the parent cosine looks like. So here would be my label, my grid. And cosine starts at the peak. So let me break this down to 4 equal parts. Goes at the peak, comes down to the midpoint, down to the trough, back to the midpoint, and back up to the peak. So that's what the cosine curve looks like, our 5-point system. And that's what our graph should look like. So it'll be a transformation of that. So here I know that the cosine is going to start at the peak. So I need to go to the equation of axes. It's shifted 360 degrees to the right. So it's going to really start right there. And if I take my equation of axes and go up 3, there's my point. Then the next tick on my axes is going back to the equation of axes, and then go down 3, so it's going to be -5, back up to the middle, and up to the peak. And over here, there's our graph. Okay, maybe as an aside, it might be some of you might want to actually calculate the peak, and so it's easier to graph. So here we could determine how the peak is really what our equation of axes is, plus the amplitude. So in this case, our equation of axes was -2 plus the amplitude of 3, and that's 1. And we do see that we have a peak value of 1. And we could also calculate a trough, because we know the trough is really from the equation of axes minus the amplitude, and then it's going down. So in this case, we have the equation of axes is -2 minus 3, and that's going to give us -5, and we do see that we have a trough there of -5. So if you like to calculate the peak and troughs, just to make it easier for you to plot those points, I encourage you to do that. So one last example here in terms of an equation. Again, we have a k value. So in this equation is the same thing as y is equal to -3. Oops, let me try that again. Y is equal to -3 cos, factor out to 4. So I get theta minus 180 divided by 4 is 45. So list off the attributes. A is -3, so I can see there's going to be a reflection there. K is 4. D is 45 degrees. And, oh, no C value. So here the equation of axes is right on the x-axis. So the period is 360 divided by K, which is 360. My K value here is 4. So that's going to be 360, which is 90. So this one is a little bit tricky because I get 90 divided by 4 and we get 22.5. Because 90 divided by 2 is 45, 45 divided by 2 is 22 and a half. So in my scale here, instead of labeling each tick as 22.5 because it could be a little bit tricky to read, I'm actually going to label every 2 as 45. So there's 90 and 135, and that would be -45. The phase shift here is 45 degrees to the right. Since my D value is positive, the amplitude is 3. So again, amplitude is never negative. It's the absolute value of my A value. In that case, is 3. And my vertical shift here is 0. So that applies my equation of axes is y is equal to 0. And for kicks, we'll just dot that, but just recognize that it is right on the x-axis. So let me graph this in red. So cosine. What does cosine look like when it's reflected? So it's the same thing where the peak becomes the trough and trough becomes the peak. So let me go back up into this graph I did before. So in this case, the peak becomes the trough. It comes back up to the middle, up to the peak, because the trough becomes the peak, back down to the middle, and down to the trough again. So cosine, that's what it looks like reflected. Oops, let me try that again. So that's what it looks like reflected. In other words, it starts at the trough and then goes up. So here we can have a phase shift of 45 degrees to the right. So it's going to, cosine is going to kind of start right there. And because my amplitude is 3, that makes the trough -3. Then it's going to go to the middle, and then go to the peak, which is 3, back down to the middle, and then down to -3. And again, connect the graphs carefully. Okay, so graphs look like that. Maybe as a side, I'm kind of picky on these graphs. What I do not want you to do, and maybe I'll do this in brown, is to draw your cosine curves like this. Because what's happening here is your graph, you're going way below the minimum. Okay, so I'm going to be picky on that, and you might lose some technical, or you will lose some technical marks if you draw your graphs like that. Likewise, with a normal cosine, you don't want to be going past your peak. I know that that's where it's starting, and sometimes we get in the habit of starting above it so that we get that continuity. I encourage you to start below it and draw it so it curves nicely, hitting that peak and trough, and then going back the other direction. So let me undo that because that's not what we want to see. Our next example, we're not given an equation, but we're given a description. So we need to pick off some keywords in our description to understand what's going on here. So here we're saying that the cosine function has a maximum of 7. So here already maximum, I can say, oh, it's the peak. That's 7, and a minimum of -3. And in this case, because we're given the peak and the trough, we can actually determine 2 attributes already, and that's what I'm going to jump to right here. What is the amplitude? So we said the amplitude is peak minus trough over 2, which is 7 minus 3 over 2, which is 4. So we know right away that the A value is going to be 2. Okay. The other thing that we get with the peak and the trough is the vertical translation or vertical shift, or what we call the equation of axes. So in this case, this is y is equal to the peak plus the trough over 2. In this case, it's going to be 7 plus or minus 3. Oh, I did the amplitude wrong. Let me come back and I thought it was 3, but it's actually -3. So let me go back and fix that afterwards. 7 plus or minus 3 which, over 2, which is 4 over 2, which is 2. So let me go back and fix that. So this is 7 minus a negative 3 over 2, which is 10 over 2, which gives me amplitude of 5. The next two ones are a little bit more tricky. The period, only because we're not giving a distance from peak to peak or trough to trough. But as I said earlier in the previous section, is that because a sinusoidal curve is broken up into 4 equal parts, what we can always determine is that whenever we go from the peak to a trough to a peak, it's always going to be half the period. And you can see that anywhere within this graph, we go peak to trough here, or trough to peak, or peak to trough, it's always going to be half of my period. And we can see that as well when we look at the sine curve as well. We get that same thing as well. So here, if we calculate the distance between the peak and the trough, so in this case, and that's why it's important here that this is the subsequent minimum. So the peak is happening at, the maximum sort of happens at minus 30, and we're going all the way to the 90 degrees. So that implies that the period in this case is 90 minus a negative 30, which is 120 degrees. Okay. And now we have to determine the phase shift. So the easiest one actually to do is the cosine, because we know that cosine starts at the peak. So in this case, we know that the peak happens at minus 30. So we know one of the maximums happens there. So there we could say that the phase shift for cos is minus 30. That implies a d value of minus 30 degrees. Okay, so let's do that right away. Let's get equation for cos. So here, let me switch back to blue. You get y is equal to my a value is 5 because I'm doing cos. Let's write cos. My k value, haven't determined the k value, so that's we're going to do that over here. This implies that k is 360 divided by my period, which is 120. So k is 3. And in this case, I know my phase shift for cos is a negative 30. So this is going to be theta minus a negative 30, which becomes theta plus 30 degrees. Remember degree sign. And our vertical translation here is 2. So that's going to be plus 2. Now, what is it going to be for sine? Sine is actually a little bit more tricky. And I'll show this to you in a couple of ways. So as I said before, the period, the amplitude, and the vertical translation does not change at all. So we could just sort of recopy all that. And really our phase shift has changed. So how does it look? So one way we could kind of see is we just draw a rough graph of what this might look like. So we know that at minus 30, let's say minus 30, that's at the peak. And then it comes back down. So here's my scale is going to be every 30, so it's going to come back down over here, right at the origin, and it's going to go back to the down to the trough, back to the middle, and something like that. So that's where a cosine would look like. And I purposely extended this part over here. So really, this is where sine. I didn't do the vertical translation, so let me try that again. Vertical translation, would have been 2. So maybe up there. So cos would have been looking something like this. So here we need to find, because sine starts at the equation of axes, well, exactly what is the x value here? So remember I said that our sine curves or cosine curves are broken up to 4 distinct parts. So because here 120 divided by 4 is 30, we know that this x value is going to be negative 60 degrees. So one of the things that we discovered is that the phase shift for sine is actually negative 60 degrees, so that becomes plus 60 degrees. Another way that we could look at this, and this will always be applicable, is that you can think of the sine curve is 1/4 of a shift to the left of whatever the cosine is. So here, a generic thing that we could think of is that, and I'll just focus on that part, this is really whatever the phase shift for cosine is. But because we're shifting this 1/4 to the left, that means we have to add 1/4 of the period. So that's 1/4 times my period, which is 120 degrees. So really, what's inside my sine function is going to be theta, 3 times theta plus 30 plus 1/4 of 120 is another 30. So really, we could, for another way to term this is that this is going to be 3 times theta plus 30 degrees. So that's another way that you could get your phase shift for the sine. Okay. So one last example, we have another word or description. So a sinusoidal function has an amplitude of 3 units. So from this, I can automatically imply that A is going to be 3. And a period of, oh, this is really nice. So it gives me the period, 720 degrees. So that implies that my K value is going to be 360 divided by the period, which is 720 degrees. And so K here is actually going to be a half. And it has a maximum of 0,0. So this one is a bit tricky because we're given a coordinate. We know that the maximum is actually the y coordinate of my point. So here I can say that the peak is actually 0 because that's the maximum value. So how can I determine the trough or the equation of axes? Well, we're given the amplitude. So because we know that the amplitude is sort of the distance between the peak and the equation of axes, we can apply that the equation of axes then is going to be y is equal to minus 3. In other words, the halfway point is going to be negative 3, and from that we determine the trough is going to be 3 away from the equation of axes, with another 3 down, so the trough is going to be minus 6. Okay, we don't actually need those values because what's more important is that we got the equation of axes. That implies my C value is negative 3. So already I got 3 of the attributes. Let's pick cosine, because we're given the peak. It happens right there. So the equation starts off as y is equal to my A value is 3 cos. In this case, my amplitude, my K value is 1/2. Theta, no phase shift because the x value of my maximum is at 0. So here I can write down the phase shift. And again, this is for cos. This is actually 0. So I need to write 0 for now, and then we determined the equation of axes is minus 3, so we want to clean that up. So really this is the same thing as 3 times the cos of 1/2 theta minus 3. Using the trick that I just talked about, how do I get sine? Well, this is going to be y is equal to 3 times the sine. In this case, I know I'm going to have a phase shift here. Theta minus 3, and again, I said above it's going to be 1/4 of my period, so 720 divided by 4 is 180, and again we're shifting this to the left, so this is going to be plus 180 degrees. So that's our equation for sine. So here I just have some pointers. So in general, so let's look at our graph. So we look at the sine curve, right? So basically here, we're saying that the cosine curve, which would start here, is really sine shifted to the right 1/4 of the period. So this is going to be x, because it's shifted to the right, we just leave it as x minus 1/4 of my period. Another way that we can look at cos is it's going to be really the same thing as sine, but because it's shifted to the left, this is going to be plus 1/4 of the period. Okay, and which is what I showed above. All right, so hopefully you'll be able to graph a function. Actually, we didn't graph here, it's just coming up with the equation, but once we have an equation, we can graph. All right, so I hope this video was helpful in order to help you either graph or come up with the equation of a sinusoidal function.